Question 7 from tutorial 6. This question is about the Fibonacci number recurrence relation, and we would like to see how we can produce this recurrence relation given the situation described in question 7. Alright, so what we will start with is to define what we are looking for. This will be our sequence. Xn will describe the number of rabbit pairs that are present by the nth month. Notice that this is cumulative. We will have to start with the number of rabbit pairs in the first month. That would be, of course, x1 equals to 1 because there will be one pair of rabbits. And then we go on to the next month, and in the second month we still would have x2 equal to 1 because the rabbit pairs have not started reproducing yet. And subsequently, we will need to add on number of rabbit pairs that are produced as we go through the months. So every month after this, the rabbit pairs will start reproducing, and each rabbit pair will reproduce a new rabbit pair. So to get the recurrence relation, what we will do is to examine xn plus 2, the corresponding number of rabbit pairs that are present in the n plus 2th month. We will decompose this number of rabbit pairs based on the age of the rabbits. So knowing the age of the rabbits in the n plus 2th month will allow us to get a nice partition of the number xn plus 2. And here is how we will do it. We will look at the number of rabbit pairs of age 2 months or older in the n plus 2th month. Notice that all of these rabbit pairs are those that are able to reproduce already. That's what we know, because once they hit the age of 2, they can start producing a pair of rabbits. Then the next thing we would look at would be the number of rabbit pairs that are born in the n plus 2th month. In other words, those that are of age 0. And finally, we also do have the number of rabbit pairs of age 1 month in the n plus 2th month. This is a sensible decomposition. Those that are of age 0, age 1, and ages 2 or older in the n plus 2th month. Now notice that we can relate the age of the rabbits to when they were born. That certainly is possible, as you can see. Let us start with the first number describing xn plus 2. If a rabbit pair is of age 2 months or older in the n plus 2th month, well then it means that it should have been born in the nth month or earlier. If you're age 2 or older in the n plus 2th month, you would backtrack by 2 months, and that would mean that the rabbit pair would have to be born in the nth month or earlier than n plus 2. Seeing that this number xn, as we mentioned before, is cumulative, we see that the number of rabbit pairs that are born in the nth month of earlier would be accumulated into the nth month itself. That's because, as you see from the question, no rabbits will die, and after 2 months each rabbit pair produces a new rabbit pair. Therefore, this number, the number of rabbit pairs born in the nth month, is also going to be cumulative, and based on our correspondence, our one-to-one correspondence between those that are of age 2 months of older and those born in the nth month, we see that therefore the number of rabbits of age 2 months or older in the n plus 2th month is exactly the same as the number of rabbit pairs born in the nth month or earlier, and this number itself is precisely the same as xn. Since xn, as we mentioned previously, is the number of rabbit pairs that are present by the nth month, which is also the same thing as the number of rabbit pairs that are born by the nth month. so it's the same thing. This allows us to get an understanding of what this number is in our decomposition. It is xn. So that is what we have found out from the question. The number of rabbit pairs in this case is just xn of age 2 months or older in the n plus 2th month. Let us look at the next part of our decomposition. It would be the number of rabbit pairs born, that is of age 0 in the n plus 2th month. But if a rabbit pair is born in the n plus 2th month, it must have come from a rabbit pair that was existing before the n plus 2th month, that is older than age 0, and it should have been 2 months old. This is to say that this number is completely determined by the number of rabbit pairs of age 2 months or older in the n plus 2th month. And we found out what the number is. It is xn. So all of these rabbit pairs of age 2 months or older, they would reproduce one new pair in the n plus 2th month. And this would account for all the possible rabbit pairs that are born in the n plus 2th month. This implies, based on our reasoning, that this quantity, the number of rabbit pairs born of age 0 in the n plus 2th month, would be derived from the number of rabbit pairs of age 2 months or older in the n plus 2th month. It will be equal because every pair produces one new pair in the month itself. Consequently, seeing that every one pair here in this number produces one new pair, it shows us that we can have exactly just so many rabbit pairs born in the n plus 2th month. That is to say, it is equal to xn. So that shows us that we have obtained yet another part of our decomposition. This number is equal to xn and is completely determined by the number which we calculated here, those of age 2 months or older in the n plus 2th month. Okay, so that will give us this number, and that is what you see here. Those born in the n plus 2th month, the number of them would be xn. Finally, we look at the last part of our decomposition, which concerns those which are of age 1 month in the n plus 2th month. Now, if they are of age 1 month in n plus 2, it would mean naturally that they would have to be born in the n plus 1th month. You would just need to backtrack to the previous month, and that would be when these rabbit pairs would be born. So we need to get the number of rabbit pairs that are born in the n plus 1th month. How can we do this? We remember that xn is cumulative, so when we get to the nth month, xn will tell us the number of rabbits that are present by the nth month. So what we should use in this case is the quantity xn plus 1 minus xn. This is just the offset. You have here the number of rabbit pairs by the nth month, and here the number of rabbit pairs by the n plus 1th month. So if you are here, then subtracting whatever was before the n plus 1th month, that is up to the nth month, you would get all the rabbit pairs that appeared in the n plus 1th month. That is to say, those rabbit pairs that were born in the n plus 1 month. So this quantity is exactly the number that we're looking for. The number of rabbit pairs of age 1 month in n plus 2 is going to be xn plus 1 minus xn. And therefore we can put everything together. So xn plus 2 has this decomposition, and the first number was determined to be xn. The second number is completely determined by the first, it's also xn. And finally, the number of rabbit pairs of age 1 month is given by this quantity as we just found. Computing this allows us to get xn plus 1 plus xn, which is the Fibonacci number recurrence relation. For the term that we are interested in, it equals to the sum of the previous two terms in our sequence. That is the defining feature of the Fibonacci number recurrence relation. And so we have solved this part. For the next part, we are interested in the sequence an, which is defined in terms of xn. It is xn plus 1 divided by xn. So we are supposed to prove a certain relation for the ans, and here's how we do it. We look at an plus 1. This is by definition xn divided by xn minus 1. We will make use of the Fibonacci recurrence relation. So xn would be the sum of the previous two terms, xn minus 1 plus xn minus 2. That explains this part of the equation. So in the next step, we simplify. We get this. And the term that we have over here is easy to recognize. It is just 1 over an minus 2. And that is the formula that we were supposed to prove in the question. In the next part, we assume that this sequence an has a limit, which is L, and it is not equal to 0. Because it is assumed to be not equal to 0, we must have the L should be a positive number, because all the values of our sequence, the ANs, are defined in terms of the sequence xn, and of course xn is always a positive number. Therefore the ANs will always be positive, and our limit, seeing that it is non-zero, must be also a positive number. It is impossible for L to be negative in this case. So we will make use of the recursive formula which we have found in the previous part, the one that we just computed. We see that L equals to this limit. That is what we have from before. But an is described as 1 plus 1 over an minus 1, using the formula from the previous part. And it is therefore equal to, by applying standard limit laws and seeing that L is not equal to 0, 1 plus 1 over L. Applying the limit laws correctly will give us this number. The thing to note here is that the limit for an minus 1 is also going to be L. And the reason is, when we take the limit as n tends to infinity, we will be sending n to infinity. But it also means that n minus 1 is also being sent to infinity as well. So as we take n to infinity, an would proceed to the limit L. And similarly, n minus 1 heads towards infinity, and so an minus 1 is also heading in the same direction as an, which is to the value L. That explains why we have just such a formula. And from this, we obtain a quadratic equation. This is the equation that we got. Multiplying throughout by L would give us this equation, and solving it would give us these two roots. And we know that L is positive, so we would have to reject the root which is negative. That leaves us with only one choice, and so L must be equal to 1 plus square root of 5 divided by 2. So that is the answer to this question. We have found the limit for our sequence an, and we have solved question 7.